Okay, so let's try to graph f of x equal x cubed minus 3x squared minus 9x plus 4 without a calculator. That's a major purpose of Chapter 4, and we now have all the tools to be able to do that. So I take the first derivative, and I look for critical numbers. So I ask myself, where is f prime of x equal to 0? And I ask, where is f prime of x undefined? In other words, where does it not exist? Well, we know that 3x squared minus 6x minus 9 is defined for every real number. I can put in any real number and get out a real number. I don't have division by 0 is the idea. I don't have division by 0. So where is f prime of x undefined? It's undefined nowhere, because it's defined everywhere. So this tells me the graph has no sharp corners. Okay? Where is the first derivative equal to 0? Well, let's just set the first derivative equal to 0 and solve for x. This is a quadratic equation, so either factor or use quadratic formula, but I know I can factor out a 3, can't I? Now I can divide both sides by 3. I can hear someone saying, where did that 3 go? Well, I divided both sides by 3. 0 divided by 3 is 0. Now, will this factor? I'm looking for two numbers that add to give negative 2, that multiply to give negative 3. Two numbers that add to give negative 2, multiply to give negative 3. That's a negative 3 and a positive 1. Okay? Now, I'm multiplying x minus 3 and x plus 1. If you multiply two numbers, and my numbers are minus 3 and x plus 1, and get 0, notice equals 0, you know one of those numbers has to be 0. Just think about it. If you're told that you've multiplied two numbers and the result was 0, then you know one of those numbers, one or both, had to be 0. So this tells me x minus 3 is 0, or x plus 1 is 0. So that tells me x is 3, or x equals negative 1. So I know that f prime of 3 is 0, and f prime of negative 1 is 0, because I set the derivative equal to 0 and I solve for x. So I know the graph has horizontal tangents at x equal 3 and x equal negative 1. Okay, those are my critical numbers. So all this work told me that my critical numbers are 3 and negative 1, and they're horizontal tangents there. Okay, the next thing I would do would be, let's see how high to plot these points. So we're not going to plot a lot of points. In fact, we're only going to plot our critical numbers and points of inflection. Let's put 3 into the graph, into the equation, and 1 into the equation, and rather negative 1, and see what y's we get. Okay, 3 cubed is 27, minus 3 times 3 squared, that would be 27 also. 27 minus 27 is 0. Minus 9 times 3 is negative 27, plus 4 is negative 23. See, you didn't need a calculator for that. Negative 1 cubed minus 3 times negative 1 squared minus 9 times negative 1 plus 4. Well, that's negative 1 minus 3 plus 9 plus 4. That's just 9. So I know that 2 points on my graph, and these are critical important points, are negative 3, negative 23. So negative 3, negative 23, and negative 1. I goofed that up, didn't I? It's positive 3, negative 23. It is 10 minutes to 1, so that's my excuse. Okay, and negative 1, 9. Okay, I know that I have horizontal tangents here. Now, here's something we've talked about before, but I'm going to show you how to organize your work here. What you need to do next is to put these critical numbers, whatever critical numbers you got from setting the derivative equal to 0, from looking to see where the derivative's undefined. Those are all the critical numbers. Put them on a number line. And you'll notice that those two numbers form on the number line, divide the number line into 3 intervals. The intervals are negative infinity to negative 1. This interval right here, negative infinity to negative 1. And negative 1 to 3. And 3 to infinity. Okay, we want to pick a test value k in the interval. Do not pick an endpoint. And we want to look at the sign of the first derivative evaluated at k. I'll explain why we're doing this in just a minute. But pick a number less than negative 1. Pick a number in this first interval. Any number, as long as it's less than negative 1. How about negative 2? Let's pick a number between negative 1 and 3, a number in the second interval. Say that's 0. Pick a number bigger than 3, say 4. Now, put this number into the first derivative. Okay? Now, our first derivative is 3x squared minus 6x minus 9. Now, I can actually say 3 times negative 2 squared is 12 minus 6 times negative 2, that'd be plus another 12, that'd be 24 minus 9. I get a positive result. All I care is if I get a positive or negative. What does that tell me? So this tells me something about the behavior of f. It tells me f increases. Now, I really didn't have to do all the work to actually plug into the first derivative to get a value. Notice when you factor the first derivative, you get x minus 3 times x plus 1, right? You really get 3 times x minus 3 times x plus 1. If I put in negative 2 for x here, I get negative 5. Negative 2 minus 3 is negative 5. That's negative. Negative 2 plus 1 is negative 1. Negative 5 times negative 1 is positive 5. I got a positive. See, I don't care if it's positive 5 or positive 15 as long as it's positive. So it's really easier to plug your numbers into the first derivative when they're in factored form. When the derivative's in factored form. Plug 0 in, x minus 3 to x plus 1. You get negative 3 times 1, that's negative. What does that tell me? First derivative is negative. That means f decreases. I input 4. 4 minus 3 is 1. 4 plus 1 is 5. Positive times a positive is positive. So that tells me f increases. Remember from our previous lesson, if f is increasing on an interval, the slope of the tangent line is positive, and therefore the derivative is positive. But if f is decreasing on an interval, then the first derivative is negative. Okay? So, I know that on the interval negative infinity, negative 1, so from here to here, the function is increasing. I know between negative 1 and 3. So from here to here, between negative 1 and 3, the function decreases. How far does it decrease? It decreases down to this point. And then, from 3 to infinity, this interval of the number line, from 3 to infinity, the function what? Increases. Okay? You know, since I knew this point was on the graph, and this point was on the graph, this is like a puzzle put together. Didn't I know my function had to increase, decrease, and then increase? Because to get from this top point to this bottom point, you've got to decrease. I'm also using a fact here we really haven't talked about this semester. Continuity. I'm graphing a polynomial here, and a polynomial has a continuous graph. There's not a break in the graph. You don't pick up your pencil. Whenever you graph a polynomial, what do we mean by a polynomial? The exponents are whole numbers. Exponent of 1, an exponent of 2, an exponent of 3. In other words, I don't have any 1/2 exponents or square roots. I don't have any negative exponents, so I don't have things like 1 over x. Here's an example of a polynomial. Graph of a polynomial is always continuous. It doesn't have any breaks. Okay? This is our graph. Now, I might not have gotten the shape really good. Okay? So, what we would do then is we take the second derivative. You know what? I'm running off the page. Let me stop and start a new Pencast.